Where's the docs again?
It's in
Are
the
they
chat, and I believe. Oh, I don't know if you also want to throw that in the mock comp channel. And okay, there you go, Johnny. Just put it in there. I will
here
pin
we
that.
go. Gracias.
So it's there as well. So yeah, so Jack and Lukash, right? Lukash?
Is Lukash here?
Yep.
I think. Okay, cool.
Cool. So since this is you guys' first meeting, I'll just kind of briefly go over what mock comp is again. The meeting recording from Monday is available if you want to watch that at 2x speed, but basically we're trying to do start from the top. DBF, we make RC airplanes for AIAA's competition. And this is basically trying to get you guys familiar with our process so that next year you can work on the competition plane. Because this year's competition, A, got canceled because of COVID, and B, is over anyway. So yeah, the purpose of this is basically just to have you guys work through a slightly smaller version of that design challenge. So you know, like, what resources we have as a club as far as like the different like code and stuff like that, and then also just get some experience with that design process. The rules for this design challenge are in the Slack. So if you go to the mock comp channel, there's a pinned section, and there's a PDF of the mock comp rules. And that's just basically in the same style as like the AIAA rules, except for like what this particular mission is. All right, yeah. So
That's a question.
Yeah, what's up? For sure.
On the app, on like a phone, how do you view pinned? Because I see like in the actual chat there's pinned, but it's not like in one section.
Yeah, so here, let me pull that up. So if you go to the, like, if you hit the top where it says like mock comp and it like opens up a bunch of info.
Oh, got it. Wait, okay. Oh, pinned. Okay, cool.
Okay, cool.
Thank you.
All right. Oh, and then also, I guess, Jack, you know me from study session, and then here I'm the lead engineer, and then Johnny is our president, and Becca, who just joined, is our vice president.
Hello.
Hello, nice to meet you too.
All right.
Sounds good. Sounds like we have a team.
Indeed. First time this year we've been able to say that. What? It's crazy having a lot of people here, so I'm excited. You are seeing my desktop now, correct?
Yeah, we can see it.
Okay, cool. I have a lot of PowerPoints open because I was referencing a bunch of old stuff as well. So let me try to find, here we go. Okay. And you guys can see the PowerPoint? All right, awesome.
Yep. Yeah, we see conceptual design 1.
Conceptual design 1. So the basic idea here, and I guess this is what you guys have probably gotten to on Monday, is you know what the rules are, but what plane do you make, right? I mean, you can literally make any aircraft. What do you do? And so the goal of conceptual design is to, at the end, have an idea of what general configuration of the aircraft is going to result in the best scoring plane. And so the first step in that is to kind of look at the scoring equations and see what they're telling you about the aircraft, right? So I've pulled these from the rules document. And so what this is saying is mission 1, if you fly it, you get 1. If you don't fly it, you get 0. Mission 2, you have the number of payloads at the top, and then you've got the time it takes to fly 3 laps and the takeoff distance in the bottom. And then you've got your ground mission. That's the time to load all of your payloads. you've got your rated aircraft cost, which is your empty weight and your battery weight. And then you've got this total score, which is your mission 2 over your ground mission and your rack. And as I mentioned here, mission 1, we can kind of just ignore. It's just a test of like, can you actually fly? Because you have to fly that first. And if you can't, you get 0 because you're multiplying it in. So. Yeah, so I guess any questions on those scoring equations? I wrote them, so it's hard for me to know if like they kind of make sense as to what's going on there. But
What's the TOLF in feet?
oh, sorry, thank you. Yeah, that's a takeoff field length. So the way I set it up in the rules is for mission 2, you basically get to mark off your takeoff distance, and you have to take off in that distance, and you get scored based on basically how short you can make it, right? Because the shorter it is, the higher your score.
Also, a question: how would they measure that on like a real?
Yeah, so they've done it in different ways. Our freshman year, they didn't actually score on takeoff distance, but what they did do is there was a really short takeoff distance requirement. I think it was like 10 feet or something. And they just put it on a ramp. And so if you didn't take off in time, you just fell. The way I have it in the
Many
rules,
teams did that.
Many teams did that. Oh God, what was it? Was it Ohio?
Ohio State.
That their plane was like 30 pounds, and it just couldn't get off the ground in 10 feet, and so it just kept nosediving off the ramp, which was
They
very
were like
funny.
drilling holes in I swear that thing could have been solid wood.
Yeah.
They go back to their tent, start drilling.
Yeah, they're like, we need to remove all of the weight. Yeah. No, so that was funny. But yeah, so for this one, I think the way I said it in the rules was basically we're just putting a block of wood where you say your takeoff distance is going to be, and then you've got to clear the block of wood to get that score. Yeah.
I got a quick question.
Yeah.
Is crates and containers, are those different? Or is that like, as I know we mentioned the Jenga blocks, but are those like two different like things, or are they just both the same?
Yeah, so 1 second. Basically what I wanted to, one of the most important things a lot of the time is building mechanisms like that are kind of niche mechanisms for that specific mission.
Okay.
And
so it's like any mods to the plane, basically.
Yeah, the way I wanted to do that is because Jenga blocks are a very simple payload. Mm-hmm. I wanted to make you guys kind of design some box or whatever that you can put the Jenga blocks in. Okay. And then that will like snap into the plane somehow. Okay. However you guys want to do that, but that's kind of what's going on there, yeah.
And then is EW empty weight and BW battery weight?
Exactly, yeah.
Okay.
Wait, so is there I'm sure this is in the rules, but is there a limit to how many crates you can put in a container or no?
No, you just have to have, I think, at least one crate per container, I think is the only rule. Yeah.
Okay, cool.
So that's going to be kind of a trade-off potentially for like later parts of the design where you're going to say like, how does having different combinations of crates and containers numbers change, for example, your like ground mission time or your like structural complexity or your empty weight or something. Like obviously none of the payload is counted in the rack, but for example, if you are doing some kind of snap-on mechanism like this, right? If you need to make the airframe have the snaps for those, and that's, you have like 200 of them, then that might, again, I drawing random crap to try not to give you guys ideas, and also because I'm bad at coming up with drawings, but like that'll just be something to consider as far as how you want to allocate those.
I have a question.
Yeah, what's up?
You said the Jenga blocks go in containers and the containers go in the aircraft. Does do you have to load the Jenga blocks into the container during the timed ground mission?
Yes.
Okay.
Yeah. See,
Um,
sorry. Yeah. Because otherwise you would want to start with like one container with like 200 Jenga blocks in it or whatever.
yeah.
Yeah. Which, I mean, to be fair, sometimes the actual DBF rules end up being like that, where there is like an obvious best answer. For all I know, you might find an obvious best answer that I haven't thought of in these equations. So
Can I clarify another?
yeah.
Do we have like a rack to put the Jenga blocks on before we put it right into the container? Technically, you haven't said that yet.
I haven't decided that yet. What I'm leaning towards is the Jenga blocks will start in like a bucket or something. If you want to make a mechanism that will assist you with loading it somehow from the bucket, sorry, I keep scrolling, like from the bucket into the plane or into the crates or something, I think that would be allowed. And I'll here, let me actually, I don't have any paper on my desk, hold on. I was gonna make a note to myself to do that real fast. So
And then also another question.
yeah.
Can we just, if we had like let's say we had like a bucket as let's say our plane's pretty big and our bucket is just like where we're gonna hold the Jenga blocks. We don't have to stack them neatly. We can just throw them all in, right?
Throw them all into the container into the containers. Oh,
Yeah.
you probably could. Yeah, I don't see a reason why you couldn't do that.
The air gap is
What is the
between
air gap?
containers?
What's the air gap rule?
You're asking me to
Is the
remember
air
the rules
gap
I
rule?
wrote?
Is the air gap rule between the shipping container or the Jenga blocks?
Hey, give me 1 second to find it.
Oh, it's between the shipping containers.
Yes.
And okay, yeah. So you did make a note that the Jenga blocks may be stacked on each other, but they can't move during flight. So they have to be immobile. So if they're just scattered in an open container, where if we give it a shake and we hear rattling, that will be something that would not pass tech inspection.
Right. So yeah, if you, that's absolutely true. I will say there might be something like there might be something to be said for that. If you think you can, I'm bad at PowerPoints. I don't present very often. Meant to annotate. Yeah. So if you have a container like this, and if you think that just kind of dumping them in is going to save you enough on ground mission time to, like, let's say, make it worth the cost to packing efficiency, and you think it won't move around too much in flight, or like at all in flight, then you can do that. There's nothing in the rules that says you can't, but you would want to make sure that it's like jammed in there so that it doesn't move. That answer everyone's questions?
Those are good questions, though. Those are
Yes.
the types of questions that we ask when we're actually reading and interpreting the rules, is what can we get away with and what can't we?
Yeah.
Well, I actually have a question. Does the aircraft have to be fixed wing or can it be VTOL?
It has to be fixed wing, or what does AIAA say? Anything except rotary wing and lighter than air, right?
Yeah, the actual AIAA is it can't be rotary and it can't be lighter than air. VTOL, I don't know what that falls under.
You know V-22 Osprey with the rotating.
That's exactly what I'm thinking of.
Yeah,
I mean,
tilt rudder. Because if you can make your takeoff field length 0, you basically get an infinite
you get
score.
infinite score. I just thought of that.
Yeah.
The limit as H approaches.
But I think that technically turns into a rotary aircraft with that with that
Yeah,
configuration.
I think it does maybe.
Because
yeah,
we can't do drones. We can't do a drone with
Right,
like we can't do a
right.
quadcopter.
Right.
So I think
What about if we use like not a jet, but like an air pump, not like or like a powerful air pump that like like that the what is it called, the Harrier uses, because that's not really a rotating blade. I guess there's rotating blades inside, but they're going horizontal.
Jack, you're thinking of a inducted fan or the
Yeah, induction.
inductive fan. Or what is it?
so.
You
I
can
think
use
you
ducted
can.
fans.
You can use ducted fans. They get really heavy.
They do get really heavy, and yeah, if you can like design a mechanism that will accomplish what you're getting at, right? Like that'll redirect some of the thrust downwards. I think that would be okay in the rules.
Yeah, thrust vectoring is okay.
Yeah. What I would caution two things. One is ducted fans are very heavy, and not only is that going to reduce your ability to fly fast, it's also going to increase your rack. So if you think it's worth it, go for it. But just that would be my hunch on looking at the rules, is that the cost to both of those things might not be worth it. Something to investigate for sure. And the other one is a little bit more on the like metagaming end of the spectrum here, but we don't have any like performance code or anything like that for ducted fans at the moment. Which means if you want to analyze like the propulsion on a ducted fan, like I can try my best, but I can't promise that I like know what's going on enough to be able to help with that. You're welcome to do it. But yeah.
No, we're just trying to figure out how to rig this system at this point.
Yeah. Yeah. And fair enough.
It's a good mentality. It's a good mentality to have.
Yeah.
Could you have a like could you have the container be the entire body of the aircraft practically, with just like very little support for the rest of the airframe?
As long as the container as long as the aircraft doesn't need the container to fly.
Okay.
Because mission 1, you do have to pass it.
Right.
And mission 1 is no payload.
Right.
Which includes no containers.
All right, cool.
I mean, you could have one of those, you could just have like a very large space cut out for the container to fit inside. Just like those helicopters that have like the hunched over, where they have like the big block that fits under them for crates and stuff.
The green helicopter from Planes.
Yes.
Yeah, exactly.
I like these planes analogies. They're very easy to visualize.
Yeah. Yeah. So anything like that is go for sure.
So on mission 1, are you allowed to fly it with an empty container?
No, because container is part of the payload.
Damn, I wanted to make the container be the structural part of the fuselage.
That is one of the things that I thought you might want to do, and so I explicitly made mission 1 no payload. But
shit, you know too much about me.
All right. Okay, so I guess what I want you guys to think about with these equations now is like, what, I guess we've already talked about a couple of them, but like what different aspects of the aircraft are gonna affect the scoring equation, and then how, like, and then other way around. Like, I guess time and takeoff distance and like number of payloads and stuff like that aren't directly related to how the aircraft flies, right? they're indirectly related and they affect it, but how do they affect it? That's kind of what I'm getting at. What are your thoughts?
I have one last loophole question.
Yeah, for
At
sure.
what altitude must this plane fly?
It has to be visible by the flight line judges.
Okay. Because if there was no altitude, we could just have a hovercraft. Just have a hovercraft.
Are you thinking like wing and ground effect and
Yeah, it just technically just like 1 centimeter off the ground.
I would, so for that, I would reference like AIAA's general guidelines. I think that they disallow that.
No
I think-
hovercrafts.
I think that there's some rule possibly for safety about how high you can, how low you can fly.
Yeah. So there are
I'd
two.
just be... Sorry, John.
Go ahead, Vlado.
I'd be worried about unevenness of the ground.
Also that.
Yeah, I think
Like-
there is some height limit for safety because there are flight judges along the length of the flight lap that
There won't be once
alert
we're
us
done
when we
with
can
it.
go. What was that?
There won't be once we're done with it.
Oh,
It's true.
yeah.
That's the secondary goal of this that isn't in the rules.
But off the top of my head, I don't know what that ceiling or what that floor, like where we have to fly above is.
Yeah.
All right, but in all seriousness, I do have an answer for your question that you were asking. Essentially, like these scoring equations indirectly influence what your plane should look like because different plane designs lend themselves to different kinds of like flight parameters. You see like a large like twin rotor plane, it has lots of storage room, but a small like single engine is fast, so you can either focus on like time for flight or you can focus on capacity.
Yeah. So twin versus.
I'm sorry, go ahead.
No, go ahead.
We also have to think about our ground time, our ground loading, because if we have a shit ton of crates and containers, it'll take a long time to load. And considering ground time is on the bottom of our score overall, that's gonna just divide that out. So I think we have to plug in the numbers and find an equation of what fits the best.
Andrew, I was thinking we have to like figure out how much time to invest in loading to get the payoff in cargo time or cargo.
So one question about the ground mission. So the rules say, right, that the blocks have to be outside the container at the beginning, right?
Yes.
But can they be, like, how are they stacked? Do we get to decide how they're stacked? Because if so, I'm going with a rectangular stack of the exact cross section of what fits in the container on a piece of paper. So I just pick up the piece of paper and pour it in.
That is a good question. I will have to think about that. I will have to pretend to be AIAA and deliberate.
Great.
Yeah. My kind of like first instinct on it is that no, that'd be mean. Okay. I was gonna say I was thinking maybe they come in the Jenga box. So
Well,
like
isn't the solution then just to shove the Jenga box in the plane, call it a container, and
I mean, I think you can't use the Jenga box, but
just
What
burn
do you
the
mean?
container off. Just like burn it off and then put it in.
yeah. I mean, like, or I mean, alternatively, instead of that, you could do something where you like dump the box over and like have a stack come out of it and then put your container over it or something like that. So I don't know.
That doesn't involve fire, so it's not.
It doesn't involve fire. Fire is always an option. Actually, I think it might be explicitly prohibited, but
Yeah, we can't. I don't think we can have fire stuff.
it's a shame.
if we burn the Jenga box and use it as fuel for an extra engine on the plane.
again, actually, no, all power has to come from propulsion. All power has to come from the battery packs. I'm sorry.
You can't attach extra firecrackers to the back of your plane, light them off.
I
Only
think
if
if
no
you
one
use them
notices.
for control and instead of for propulsion, I think you can.
Oh, really?
I
You just have a
don't
JTOW
think-
rocket on the back of our
Yeah.
plane.
I don't think that's disallowed by virtue of nobody's tried it.
Exactly. That's what we're here for.
Yeah,
You know,
exactly.
Break new ground.
So on a slightly different topic, as much as I really truly do like this topic, is there any limitation on high lift devices?
No.
Great, because it seems like that could be useful for getting high speed and good takeoff distance at the cost of build complexity that doesn't matter since we're not building it.
Hey, CAD complexity.
But also, if we have high lift devices, as we increase our speed, just gonna get more and more lift, which is not really.
Well, the idea being to retract them for high speed flight.
Yeah. So. Okay.
So I might be out of my league here, but what the heck is a high lift device? Are you guys talking about like a ramjet or something?
Talking about like
No.
flaps and slats to
Oh, like
Yeah.
wing modifiers, like modifying
Yeah.
the airfoil. Okay.
Yeah.
The
In fact-
ramjet, I was way off.
I
I
would.
mean, if we can get one of those.
It does have to be electric.
Well, so it has to be from the battery. It didn't say electric, right? It just says from the battery. So if we burn the battery,
Can
That
you use
is,
we can use
believe-
a hydrogen fuel cell battery and take the hydrogen out and just use that as fuel. Could work.
Hydrogen batteries are not
they
allowed.
are not allowed.
Aw.
Unfortunately, we have a choice of 3 batteries, and the only logical choice to use is LiPo batteries because the other two suck.
Don't constrain their design space. You can use a NiCad if you want.
Can we have
Triple A's.
this in water use like both the hydrogen and oxygen as a combustion? Because that is coming from the battery.
I mean, lithium batteries burn pretty well, right?
They do. They are very combustible. Except you might like fly by the row of like flight graders and just like give them all like cancer as you like fly by like pumping out like black
I feel like
lithium
they're
smoke.
really not gonna like us at this point.
Yeah, and remember, I am the judge for this one, so. No.
So you're saying you're lucky that we're not actually building it.
Yes. Yeah.
She called it the SS Health Hazard.
No, you gotta crash it into USC's van. That's the end goal.
Another thing would be like the dimensions, which like affect the weight, because the weight's like a big part of like how the plane's gonna fly.
Hold on. I wasn't annotating, but it still let me write, and now I'm confused.
You're good.
Could you elaborate on that, Preston?
Just like the weight of the plane and like the dimensions, like how big we make the plane and like is gonna affect the weight. Like we're gonna have to have like different parts of the craft, like the wings, like how big like the wings are gonna be. Like where we're gonna be able to attach the payload, where the battery is gonna attach, like all that stuff. We have to like account for that when we're like designing the actual like airplane itself.
Yeah.
Do we have someone who knows how to actually fly an airplane quite well? You know how, Andrew? I did not know that.
I've flown RCs and I've flown Cessnas.
Oh, really? I
are
can
you
fly
an actual
drones,
pilot?
but
No, I want to be. My friend is actually. No, I did a summer camp like 3 years in a row, and we went up.
Nice.
Very cool. Yeah. So we do have a pilot at the moment, but we want you guys, like Andrew already has experience, but if you don't have experience and want to learn, that's something that we want to try to do next year is train a new pilot for the club.
Yeah. Yeah, so dimensions are super important. In particular, especially this early on, wing size is something that is going to be really important. Yeah. Anything else that you guys are seeing in these equations?
Can you put like air balloons in? Because it can't be.
Nope.
Oh, it can't be lighter than air. So as long as it's just one micro like AU atomic mass less than an air molecule, then it still technically works. Unless
my worry with that is just that I think it would be hard to get enough helium to get a useful amount of lift without making the thing very big and therefore picking up significant drag. Like, I don't know if we'd get too much, if we'd be able to get enough to make a difference before we start undoing it by making a blimp.
just an inflatable airplane. You just have somebody in the back with a pump.
Okay, I'd want to do that for different reasons.
Laird, I was thinking it's not kind of obvious on the material that we build the plane out of will directly affect the empty weight, and it will affect time and everything else as well.
Yeah, because adding on to Peter, I think Laird or John, is it Johnny?
Yeah.
Yeah, Johnny.
Okay, I think one of you were saying that previous planes were like balsa wood, and oh damn,
Too high, volume too high, Laird.
yeah, and canvas, I think. So I think adding on to Peter's, like, I don't think we're gonna have like metal, a whole ton of metal, unless it's a necessity.
Although aluminum could make it quite strong in case we crash, but probably with Andrew's flight skills, we might not. I'm not confident though.
I mean,
so we do have a variety of materials that we use in plane construction. We have balsa is the main one that we do structures out of, where we sometimes do our prototypes with foam wings. And then there's different types of foam that we use. We also are doing more research into composite materials. So there's there's a whole slew of considerations with composites that you have to do. We do have some metal parts, but they're usually like for servo arms and things like that. So they're usually small. But that is a weight consideration. Do you want to have, like, how do you want to have your control surfaces actually controlled? Do you want this type of control over another type? One may be more reliable, but one may be lighter, things like that. And we do, yes, use plastic 3D printed pieces. So we do use a wide variety, and it is something that does have to be considered, not necessarily heavily in this stage, but it is something that is considered in the scoring analysis. And Larry, we can't hear you now. Or at least I can't.
I can't either.
Hello?
Okay, you're back.
I hate Zoom. It happens like all the time to me. I don't know why, but regardless. Yeah, so material actually does come into scoring analysis to some degree. At some point we'll be looking at doing some kind of at least conceptual weight buildup in today or on Saturday. So, and that's absolutely going to have to do with like which material you want to make it out of. And then Becca will be talking more detailed about like this stuff in the detail design section, for sure.
Also, very quick question.
Yeah.
For our ground ground time. We could have like multiple different crates to clip on, but we could have like 3 or 4 people packing those crates, not just one person, right?
One person.
One person. Damn you.
Yeah.
What are
That's
the
a good
limits?
sleight of hand.
Indeed.
What are the limits on what the crates can be like? Which is to say, can they have like an auto loading mechanism?
But nothing says you can't.
Okay, so just that it would be hard.
Yep.
I think Becca's tweaking out.
Scree.
Yeah, what is that, Becca? What was that?
That's my little sister.
Oh,
Say hi. Does she want to help design the plane?
We can put her in the plane.
Payload.
Make her fly it from the inside.
No.
I think that's against the rules.
No humans in the plane. What? Terrible.
It's not prohibited in the rules I wrote. AIAA might not allow it though.
Well, I don't know. I feel like it would be hard to fit a
Your takeoff
person into a plane within the rules.
your takeoff distance would also
with that mentality, it is.
Like, isn't the battery capacity pretty limited?
Yes, that
Could
is
be
that
human
is-
powered, right? Because human can eat a battery and then
I don't think the human would be very happy after eating a battery.
No.
I've never eaten a battery, so if any of you have, I defer to your experience.
What's up, Peter?
So we've been on the site for like 20, 30 minutes.
Mm-hmm.
Could we like move it a little bit?
Yeah. Yes. Okay. So here I'm gonna save this. There we go. Okay. And then clear all drawings. Okay. So yeah, this is basically the same process that I did when I was figuring out what I wanted you guys to like think about here. This is the one I came up with, pretty basic. The main parameters that why doesn't Control Z work to get rid of those? Whatever. The main parameters that I saw and that we typically use for this kind of scoring analysis are the takeoff weight, the power, and the wing area.
sorry about that.
What's up?
His phone just went off.
Yeah, my phone.
Sorry, no worries. Okay, so, and the reason these are kind of critical, we'll get to more details on that in a second, but they affect the time for mission 2, the takeoff distance, the wing area affects the empty weight, as we talked about, as far as like the different like the material buildup and stuff like that. The power that you're going to draw affects the battery weight. Both of those, which are in of themselves scoring equations or scoring parameters, also affect the takeoff weight, as along with the payloads, right? So it just kind of, one of the things I did this year to prepare to like try to figure out how to even tackle scoring was make this kind of diagram. And this is very like simplistic. Like there's a lot of other variables that are involved. For example, I haven't mentioned like drag or anything like that here, but for like a conceptual overview, this works pretty well. Yeah. Any questions on what I have drawn here? Any of the variable names or anything?
What's GTO?
Takeoff distance.
Okay, perfect.
Yeah. TO is usually takeoff. So takeoff weight and takeoff distance. Sometimes you'll see STO, but oh God, I keep writing things and then trying to erase them and not being able to instead.
Yeah, I feel like if we're using S for wing area,
Exactly. Yeah.
like we also have World Trade Organization as one of our inputs.
They can deal with it. They're not going to sue for trademark infringement. All right, yeah. So
I mean, we're not
Yeah.
getting this one stuck in the Suez Canal. They should be fine.
we could do that. But, all right. So yeah, as I kind of mentioned, the place we want to start is usually with the fewest number of variables. So there's those three variables that I mentioned that we usually want to design to, the power, weight, and wing area. And things like this, and a lot of the other details that we were talking about previously can kind of come later, because I mean, the name of this presentation is conceptual design, right? And so quick anecdote, when I started doing scoring analysis and like conceptual design this year, my first instinct was to take all like 20 variables that I could pin it down to very easily and just iterate through a massive space of all 20 of those variables. And my computer didn't like that at all. Like I put it into a very basic, inefficient script and was just like, go through every single possible combination of an airplane. And it was like, here's like 100 gigabyte file that you're not going to be able to do anything with because it's too big. So you got to narrow it down to some degree. We'll talk about in a second. Often you can even narrow it down more than this by considering the power to weight and wing and weight to wing area, which are usually called the power loading and the wing loading. And those are terms that if you have like RC experience or whatever, you've probably heard before in that they kind of describe how the aircraft performs. And so with this, we kind of want to answer questions like, or I guess I have a slide on this later, but yeah, those usually give us a really good idea of how our plane will do. From just these and some other assumptions about the aircraft, you can actually calculate the like flight speed and the takeoff distance and stuff like that. And all you need is these two parameters. So any questions on that stuff?
Would you also reasonably easily and without making your computer dislike you be able to like add a little bit of like a parameter for dealing with high lift devices that essentially like changes, like lets you use two coefficients of lift or something for
Yeah, so there are definitely ways you can do that.
like calculate the takeoff with
the way I would think to approach it is, first of all, one of the ways I like to visualize stuff like this is just by thinking of a design space. And one of the best things about having two variables is that your design space is easy to draw. So if we draw like wing loading and power loading here, what we can do is we can calculate, like, let's say the flight time, or like, yeah, flight time at a grid of points in this design space, right? And then we can figure out which of those has the highest score, right? And design there, or potentially, right? Now, you can also do another one of those, right? Same variables, except instead of flight time, you're calculating takeoff distance. Right? And so you can basically do that a bunch of times. And so if one of your assumptions going here is like a CL max of like, I don't know, 1.1, fairly standard, but you want to have a high lift device for the takeoff distance, you can just plug that in to this one. So you can have a CL max of like, I don't know, 1.5 or something with your high lift device. And you could do those calculations.
I think we can do more than that if we're going like double slotted flaps and slots and stuff.
Whatever high lift devices you want to do. Again, as was already mentioned, there's a trade-off with complexity. So the higher CL you want to achieve likely the more complex device you need, but not necessarily. So yeah.
And then
yeah.
what's the method for like determining like how far up on the wing loading and power loading you can go before it stops being a plane you can actually build?
That is what we're getting to. Yeah, we're getting there. Suffice to say, there are limits. Some of them are easy to do, easy to plot in what we call like a constraint diagram. So, you know, the max takeoff distance is 50 feet. And that might look like a line here, right? 50-foot takeoff. And then the maximum time that you can take, like there's a 5-minute flight window. And that might look like 5-minute flight window, right? And so you know that you're gonna not be able to do anything in here, right? Where it gets a little bit more complicated is the battery constraint. You can't have more than 200 watt hours. And that doesn't directly translate to a curve on the power to weight and wing loading chart. Because that has to do with the power itself, not the power divided by the weight. Like it doesn't really care what the weight is. So that will, what it'll do is it'll make some of these points that are left have a lower score because you'll be constrained by other factors like the battery weight and stuff like that. And so with that remaining design space that you do have, you can usually calculate some kind of score contour. So like maybe that's, you've got like increasing curves of how good your plane is going to score. And then you want to design to this point right here. That was a terrible star. There, that's not better, but whatever. Did that make sense? Okay, cool. All right. I'm gonna save this and not draw. So I said some slides from Noah. What I didn't realize is all of his slides were really good. So I basically just put his slideshow from our mock comp in here. As I mentioned, like we want to answer these kind of questions, like how fast will a, or like how quick, like what distance will a 3.5 pound plane with that wing area and that wing and that power and stuff take off, and lap time and stuff like that. So that's the key premise of what we're trying to do. There's really 3 conditions that we're worried about. There's steady level flight, which I have up here. And then I guess what other conditions, like flight conditions, do you guys think we care about for this
Turns.
Turns.
When whoever's flying forgets that they're on task and starts doing aerobatics.
Let's take off and does landing count at all?
It can if you want, but I personally don't see a reason to worry about it just because you have as long to land as you need. So
if you still have battery.
If you still have battery, yeah. If you need to emergency land, maybe you want to consider like glide ratio or something like that. But
also, I don't think we're landing.
No, you're not planning on bringing it down.
We just need to figure out how to change batteries mid-flight.
Okay. Well, you could have a servicing aircraft. Yeah. So those are the 3 conditions that we really care about. The easiest to deal with is steady level flight because it's got a very nice free body diagram. Lift is weight, thrust is drag. Does anyone know like the lift equation?
Say again.
I feel like I've learned it in 215. I just have it in my notes, but I don't know it off the top of my head.
Well, by the end of this, you will. But yeah,
It's
what's up?
half S density V squared coefficient of left, right?
Yeah, exactly.
Probably put those all in a order that you're not gonna like me for, but I can find something better for you to not like.
I would just move that over there. Other than that, you're chilling. And only because Q is your dynamic pressure, which is 1/2 rho V squared, which is just a thing that we deal with a lot. And so we like to keep those terms together. But other than that, it doesn't really matter.
Right, yeah.
Yeah. And then what about drag?
Same thing, but swap it for coefficient of drag.
Yeah, exactly. I'm doing your order, whatever. See, Lukash. Okay, so yeah, that's your basic equations is lift equals that, drag equals that, and then conveniently weight equals lift equals that, and then thrust equals drag equals that one, right? Yeah. Any questions on that? This is gonna come up a lot because it is very convenient for modeling to just assume steady level flight. So, all right. Yeah, so y'all beat me to it. We got those equations, and I just defined the variables here in case you need them. Oh yeah, something important to think about is what those coefficients of lift and drag are. This equation will never not be true by virtue of the fact that CL is defined to make it true. So that comes in handy when you know the lift. You know that the lift is the weight, like the takeoff weight. And you know everything else. You know your air density, you know your velocity, you know your wing area. But you just don't have a CL. You can just calculate it, right? Like that CL is driven by what you need to sustain the lift that you're at. Now, if you then get a CL that is 5, then you know that you just can't fly in that condition, right? You can't fly a 55-pound plane at 10 meters per second. I don't know why I switched to metric. You know, with whatever wing area, like you just can't do it. And that is kind of dependent on like your airfoil and stuff, but there are some decent assumptions you can make for like quick modeling and stuff for a CL max. But yeah. Any questions on that? Okay. Drag. Parasitic and induced drag. Parasitic drag is like skin friction and induced and interference drag, although we don't deal with that a whole ton. And that just comes from like the shape of your airplane. And then induced drag comes from the fact that if you have an airfoil at some angle of attack with air coming in here, right? Again, ludicrously large angle of attack, don't worry about it. You've got a lift force that does come up normal to your airfoil. But we don't care about anything in that direction. We only ever want to know the like vertical and horizontal components because that's our lift that we care about and that's our drag that we care about. And so this drag is our induced drag. And as you can probably tell, that induced drag is dependent on the lift. And that's why it's so great that we can calculate the CL from calculate the CL from like our flight conditions, our weight and our density and our velocity and our wing area. Because then we can also calculate our drag. And the way we do that is with a parabolic drag polar. I did not mean to cross that out. Yeah. Parabolic drag polar. Which is defined by this equation. It is not right, but it's very close, and it's close enough for all of our purposes. That's why Dr. Drake doesn't like it, but like it works pretty well for everything that we need, especially in conceptual design, where we're not going to be perfect no matter what we do. We just need to get a general idea of what the aircraft looks like. Oh my God, sorry. I just looked at the time and I thought the meeting started at 6 and I was confused that we had been going for 2 hours, but it's only been an hour. Cool. Okay.
Can I make a quick note?
Yes.
So if you do have to leave, this is being recorded and should be up. We have a new club YouTube account that our Monday meeting recording has been uploaded to, and this meeting will be uploaded, and all subsequent meetings for the mock comp should be uploaded to all important ones. So all the ones where we're going through a presentation. If it's just the team working through design and stuff, I don't think we'll be recording that. But when we go through a presentation, that will be uploaded along with the presentation slides. Those will be available in the Slack. So if you do have to leave, you're not going to be, you won't miss content. If you do have to leave, you will have some way of rewatching it.
Yeah, good note there for sure. Yeah. So any, or I guess I should mention, Peter and Vlado, right before we started mock comp, were helping me work on code to do a good drag buildup in conceptual design. For now, we can just assume like whatever value you want for CD naught. As it says here, usually it's between 0.02 and 0.04, and we just kind of go with it. If you look at this equation, there are 2 other parameters that aren't defined here. There's this E and there's this aspect ratio. The E is the worst thing because look, lowercase e is taken. We have an E and it's next to pi. It should just, whatever. Oswald efficiency is E. That has to do with if you take your, like, if this is your wing, like looking from the front, an ideal lift distribution, oh God, that's terrible, but it's like elliptical. Pi does like engineers, pi equals e equals 3. Yeah, so a kind of ideal lift distribution is elliptical. That is not what we almost ever get. We usually get something, A, we have a fuselage, which makes that not happen, and B, we're flying like a non-optimum wing. We'll get something like this, which is kind of far from that ideal distribution. And the efficiency, the Oswald efficiency, is basically the percent error between those 2 distributions. Actually calculating that is something that Jake might talk about in the performance section, or I guess in the like preliminary section. But for now, we can just kind of assume a value based on generally how we do. Because again, we're trying to ease the conceptual design process to get an output. As I mentioned on Monday, the most important thing is getting a product. It doesn't need to be a perfect product. And so with stuff like this, the Oswald efficiency and the drag coefficient, it is often more important to just pick a value. And if it needs to be changed later, you can change it later, than to like make sure that value is perfect all the time. Yeah. Aspect ratio goes back to what we were talking about on that brainstorming kind of slide, where we were talking about the wing geometry and like dimensions and stuff. The wing area is the most important thing because it's in all those like lift equations and stuff. But the aspect ratio is also very important. Because it is in the denominator of this equation, higher aspect ratio wings have lower induced drag. But they are also often harder to build, so you can have like, or you end up with like not being able to turn as sharp or whatever. And so last year, we wanted to do really low aspect ratio wing. And so we had an aspect ratio of 1/2. And this was the plane we had to make. And it was not great. It didn't look like a plane. It looked like a goose, which is what we called it. So we usually try to stay in this range. But again, if you have good reason to not do that, pick a different number. But and this will probably be calculated based on the actual code that you will end up writing. You probably won't have to make an assumption about that. You'll probably be able to figure it out. Or you can make an assumption about it, whatever you want to do. Yeah, all right. So this is what the drag polar looks like. Also, I just realized, like, yeah, you guys have seen this or the sophomores have seen this in 215. But yeah, so this is the part that we really care about. And your max lift over drag is your most efficient because you're getting the most lift for the drag that you're sacrificing. So often you want to try to aim for that point. Sometimes you don't have that luxury, but yeah. So one of those other inputs that I was talking about was power. Power is in units of basically work per time. So it's basically if you apply a force, right? If you've got a block and you apply a force of 1 Newton to that block, over a distance of, let's say, 3 meters, right? And then you stop. What do you know from just that? Sorry. First of all, apologies. I slipping into study session mode there. You do that, and then if you do that for, let's say, 5 seconds, right? Then your power is going to be like 1 Newton times 3 meters, or over 5 seconds. Whatever, 5 seconds. If you have an object that is traveling at a constant velocity, right? So there's a net force of 0, right? But you've got these two forces. Let's say, I don't know, let's say this is thrust and this is drag, right? And we're moving this way at a constant speed. Then you can find the power being done, like being exerted by both of these forces by taking the thrust times how far it moves. I'll call that d or whatever in any given time unit, right? And this is just the speed. So the power that your aircraft is like the power that your aircraft is both using and exerting to fly at a constant velocity is just your speed times your thrust, which is equal to your speed times your drag at steady level. The reason we want to do this is because of this other fact, that power can also be easily calculated for your battery. So if you know what, let's say, voltage and current your battery is drawing, then you can figure out how fast you can go. The problem is, at this stage in the design process, you don't know that. But if you know the power that you want, you can pick the propulsion system later to match that power. And so if we just set a power somehow, then we can find a propulsion system that'll actually set that. And that's a more of a problem for preliminary design more than conceptual. Like right now, we just want to know what power our aircraft is going to draw. That make sense? Okay. All right. Any other questions on that? Okay.
Wait, so
Oh yeah.
what, like there was a, what was it, 200, like really, what was the battery limit for drawing?
Yeah, so the battery limit is 200 watt hours.
Mm-hmm.
So what you'll notice is that watt hours is a terrible unit. It's just awful. Watts is metric, hours is nothing. Nobody uses hours, but that's just what they use for some reason, and we'll have to live with it. So if power is energy divided by time, what is watt hours? Like, what is it a unit of?
Isn't it power?
Energy.
It's energy, right? Because it's power times time, right?
Right.
It's just in shit units because it's in joules per second times hours, right?
Yeah.
So if you want to convert this to joules, you just multiply by 3600, which I often have to do in propulsion. Or if you want to convert it to like some units, like, I don't know, like foot pounds per second, something like that.
Can we not?
What's up?
Can we not convert it to that?
I mean, imperial units is better, so
Bullshit.
I stand by that, unfortunately, but I've come to love them and hate them. But yeah, so if you have this amount of energy and you draw some power, you can figure out how long you can fly, right? And that's super important because if you know, oh, I want to draw 8 kilowatts, right? Well, that's going to give you 1.5 minutes of flight time, right? And that might not be enough, and that's at like 100% efficiency, which you would never actually get. So that probably wouldn't even be enough to fly your laps, right? And so that's why you can't just have an overpowered plane, is because the trade-off against that energy limit is pretty high. So yeah. Any other thoughts on that? And also, did that answer your question?
I forgot my question, but I liked what you said, so I think it'll probably be a yeah.
Cool. All right. Sweet. So, we don't need okay. But yeah, this is the idea. This slide was made before we had lipos. So if you have a really shitty battery and low current, then you don't have a lot of power. But we now have the ability to have better batteries with more current. But yeah. Yeah, don't need to go over those slides. Yeah, so this is the key thing here, is that you want to try to predict how fast you fly. Turning is something that I'm gonna leave up to you guys, how you want to deal with it.
Good luck.
Good luck. Turns suck. One of Jake and I's research projects this quarter is to try to figure out how turns work and to try to make code for the conceptual design to have turn analysis be more rigorous. There's some code available that you can probably use. It just makes some assumptions that are probably okay, but might not be okay. You're also more than welcome to just pretend that a turn is steady level flight, but longer. Like it has this, arc length or whatever, and you can just like, as long as you're clear about what assumptions you're making, you can do what you want.
Didn't you technically do steady level flight and just use your rudder?
It still isn't steady level because you still end up banking.
Even if you intentionally don't bank and you very slowly turn.
Oh, fair enough. Yeah.
With only your rudder, how do you know how big your turning radius is going to be?
Does that matter?
Well, wouldn't that be,
if you want to know how long your distance you're flying is, then yeah.
Wouldn't that also be flying in a skid such that it would be
but minor details.
Drag.
Like the reason this matters so often and so early is that when you're trying to determine the fastest plane, it helps to know, or I think for the fastest plane, you don't need it as early, but if you just want to know how many laps you can fly in a certain amount of time, which is related but not identical, then you got to know how long a lap is. And you can't figure out how long a lap is until you know how far you fly in a turn. And it's bad.
Yeah. That turns suck.
If you think you have a solution, please tell us.
Yeah, right. And there's definitely, there are solutions, but a lot of them aren't geared towards the type of planes that we will like to fly. Like a lot of them are talking about, commercial airliners where you want less than 1.2 G turn or whatever. And like, we want to turn as fast as we can because we don't have people inside that we care about squishing. So like there's not a whole ton of analysis related to that outside of like fighters and stuff like that.
Lots of it's classified.
Which I was just gonna say a lot of that is classified. So
yeah, so if you can get any of that, please tell us.
Yeah, it's true. It's true. You probably shouldn't give it to us if you can get it though. But yeah.
No, you should.
We promise we won't tell anyone except the DBF report judges.
Exactly.
We won't tell them either.
Oh, we've got to put it in the report.
I mean, they probably won't read it, but
that's something else.
Yeah. So yeah, one of the best ways to do this kind of conceptual analysis is to use what we call excess power, which combines everything that we've already talked about. So your excess power is, you basically set some max power and I'm just going to leave that on the eraser and just only use annotate. You set a max power and then you increase your velocity until your excess power is 0, right? So if you have a like velocity versus power curve, you set a max power like this. And then remember that this Q, I don't know why they would write it in terms of Q, because this Q is hiding a 1/2 rho v squared. So this term,
lazy.
It's true. It's true. This term is really 1/2 rho v cubed CDS. And so you're going to get a velocity versus power curve that's essentially a cubic function that goes through the origin. And that's your power drawn by the aircraft. And so you're going to fly right here, right? You're going to fly where your aircraft is taking as much power as it can get. And that's the speed that you're going to go. And so if you set a power, you can calculate a speed as long as you assume, as long as you already have a wing area and you assume a drag coefficient, like a parasitic drag coefficient. You can calculate the induced drag coefficient using the drag polar that we already talked about. And so, yeah, it's pretty much all you need to assume is you need to assume that, and then your like Oswald efficiency and aspect ratio for the drag calcs. But then other than that, you can just set a power and solve for your flight speed. You can do the same thing in a turn. We can talk about that in more detail probably on Saturday. And it's a simplistic turn model that we've used for a long time that we can keep using for this mock comp. But and then, yeah, we'll see why in a second. Useful later. Key for just take my word for it for now. But if we divide everything by weight, we get some really useful equations. Yeah. Any questions on that stuff? All right. Now for the place where we use that. So back when I was talking about design spaces and like you want to try to minimize the number of variables. All right, see you, Jack. We had our wing loading and our power loading. And both of those are functions of the weight. And so if we do what I said in this last slide, and we divide everything by weight, remember that this here has an S term in it as well, right? We've got that 1/2 rho V squared S CD times V, right? So if we divide this by the weight, we've got this S over W, and we've got this P over W. And so when we go over here, oh, and in our CL formula, we've got wing loading there too. So then we go to shit. Okay, fine. They didn't do the equations that I wanted, but that's okay. If we actually kind of work through this, what we'll see is we have also, can I just do no. Fine, okay. We've got our power to weight ratio minus 1/2 rho V cubed CD times S all over W. I'm going to move this to the bottom. So I'm going to say P over W minus 1/2 rho V cubed CD over the wing loading. And then again, also, this CD is a function of CL, which is a function of the wing loading as well. So we can see how, and that equals 0. So we can see how, like, just knowing those two things, we can solve this equation, set it equal to 0 and solve for the velocity. And that's what we do. So, okay. Let me pull up another slideshow here. Oh, sorry. This is an example of a fairly basic constraint diagram. I don't know what constraints were actually used to generate this, but this
Take
curve
off and
here.
something.
What's up?
Take off and something.
Sorry, yeah. So this is takeoff, and this is a speed, right? This is I don't know what speed it was, but they set some speed, maybe like something like 50 feet per second. And at every point, they calculated, like at every point in this entire grid, they calculated that speed. They calculated the speed, and then they connected all the points where that speed was 50. And that's a constraint. So if you want to be faster than 50 feet per second, you have to be somewhere up here. Similarly, if we go back to
Well, faster than 50 feet per second is anywhere above the blue, but faster than 50 and meet the takeoff
Sorry,
requirement is above the blue, and then also above the red. How you had colored in your previous statement should have been all of above the blue.
yes, you're
Just
correct.
Yeah, Laird.
I know. I'm sorry. Here, fine.
I didn't want
Above
any
Let's go.
50
confusion.
feet per second. Above 50 feet per above 25-foot takeoff distance. Both.
Why would we use a hard constraint for 25 though?
This
Why
is
would
in
we
just
the
use a
rules.
hard constraint.
this is just a
50?
random example. There is in the rules a hard constraint on 50. So you would want to have a constraint there. But the other side of this chart is that, again, you would also have a score contour, right? And so maybe your score contour puts a design point here, and maybe the takeoff distance here is 5 feet, and the velocity is I don't know, 100 feet per second. The fact that it's in here means that you meet the bare minimum, right? Yeah. The fact that it's in here means you meet the bare minimum requirements. And then you also get to use this design space of wing loading versus power loading to iterate through a bunch of scores, right? And so if you calculate the takeoff distance and you calculate the speed and you calculate how like the optimal weight for each of those points and figure out how much payload you can carry and figure out how long you can fly, make sure you can meet the 200 watt-hour limit. You do all that, you can calculate a score at every single point. And that's your goal, is to use these parameters to, at every single point, figure out all of the different scoring parameters. And that's why what I asked, that's why I asked you early on to brainstorm all this stuff. Right? How do these different parameters relate to things like your power and your dimensions, your wing area, and your weight and your power, right? You had all the things in here, your time versus capacity trade-off. That's what this is at each of those points in that design space, you want to figure out all of those things to the best of your ability, which is admittedly probably not going to be very good because you don't have a lot of details, right? But you can get a good idea fairly quickly using just 2 variables and a bunch of equations, and that's kind of the goal, and that's what you guys are going to be working on Saturday. Is doing that. And so you want to get a point on that wing loading power loading diagram with the highest score, and then depending on how you end up doing that, that'll probably also tell you a bunch of other stuff you want to know about your about your plane. That'll probably also tell you a bunch of stuff about like your payload and your weight and stuff like that. Yeah, any questions? That's where I'm going to stop, because this was a lot, and Jake probably wants to talk about configuration stuff, unless he also wants to do that Saturday.
Bold of you to assume. I mean, I can a little. I'm
It
not
is
extremely prepared, but I can just talk.
You're welcome to do that. My inclination is that this has been a lot today. And I think I want to take the next 20 minutes to let like everyone kind of think about what you want to do as far as the actual mock comp, like using this information to actually kind of brainstorm ideas for scoring analysis and stuff for Saturday. That's my thought, but up to you guys.
Yeah, I think it would be beneficial to kind of contemplate what we learned today on what we were talking about Monday, because you should think, did some of the ideas we talked about Monday, the stuff we now know, does that contradict any of our ideas that we Monday? Some of the design ideas that we brainstormed on Monday may or may not have been, some may have been like had pros of what we learned today, and some may have had cons associated with them, with power, with weight, with the air, like wing area and things like that. So I think this was a pretty heavy presentation, where I think it would be more beneficial to reflect on that than go into a whole brand new topic, and then give Jake the beginning of Saturday, if you're okay with that, Jake.
As long as I'm awake.
We'll call you.
All right.
It's true. I'm the alarm clock.
I mean, people can also just ask random questions at any time in any place. So
yeah,
also
Jake. Jake is always up.
Oh yeah. If you're just like, if you have a 3 a.m. plane question, hit me up. I will probably answer in like less than a minute.
I'm usually up as well, but Jake takes it to extreme over me.
Now, if it's between like 9 a.m. and 11 a.m., the odds are not as great that I'm going to answer.
Indeed.
Well, I'm usually up around that time. So if you do have questions and I'm able to answer, then I can answer at that time. But don't let a time be a constraint outside of meetings to ask questions.
Yeah.
But did anyone have any questions about today, or any thoughts from both Monday and today, like I was saying?
Yeah, I was thinking my idea of that giant ass plane is not going to be a good idea.
That's what I was gonna agree with.
Yeah, it's a little bit big. But I was thinking, and I don't know if this could be a good idea for the rest of the discussion, but having a plane where we have kind of like, let's say we take like a normal plane, chop like the middle section out of it, maybe like right behind the wings and back, or just in like halfway between the wings, as our space to hold a container, and then have like very structurally sound like rods or something to hold on the tail, so that doesn't break off during flight, because it would have, I don't, is time a constraint on our flight for the first flight? Okay. And
No.
that would, it would just,
You just have to complete a lap in 10 minutes, right?
You have to complete 3 laps in 5 minutes, but
Three laps in 5.
really shouldn't be, you shouldn't butt up against that.
right. So I think we could easily do that. The only thing I'm concerned about is having enough lift with that idea and loading for the ground time.
Andrew, could you describe the plane again?
Yeah,
Probably
so
a little bit of time.
it's kind of like Oh geez. Look in the docs. You see how like on the green you can kind of take off that bottom section of
Just 1 second. Let me get on the dock.
of the helicopter. Just do that. Take off. So make that like airframe into a plane. Have wings coming out of the top. So it's kind of like. Here, let me just find a picture on the internet and see if I can.
Like the belly of it, almost like the
Yeah.
underside of it.
Like
Okay.
the entire belly is just taken out, and that's our container, and that can clip on, or something around.
Peter.
So it's like a plane with a U channel, like a C channel for fuselage.
Basically.
Okay. I mean, that could work. How does that? That doesn't affect us too much aerodynamically, right?
No, because the container would basically be the airframe, or basically be like the fuselage for the plane when we have it on.
So does anyone have any idea of how to estimate ground mission times?
No, that's a good question.
I think it would depend on how we can put in the stuff. Because if we can like,
Yeah, true.
Right, then we could just slide it all into that giant container.
Yeah, that was like the thing I suggested about at the beginning with the paper.
Right.
So like we just need Laird to let us go with whatever definitely not cheating ideas we can come up with.
Everything that you guys have said so far sounds good to me within the rules.
Yeah.
Does that count as an authorization to do the paper thing?
Yes, that's what he said.
That is what I said, although no, I might. Can you run it by me again? I thought maybe I missed it.
I think I'm thinking now that I have authorization, I'm not going to give you a chance to get back.
Sadly, he's recording it, so.
It's true. It's true. All right. Well.
Sadly, though, he also has now recorded himself saying that I can.
On the plus side, Laird has much higher response rate than AWA.
Anyway, it was that if you like start with the blocks stacked so as to fit into the container and sitting on a sheet of paper so you can pick them all up and drop them into the container as a unit to effectively make it so that you can load very quickly.
Yeah. I mean, I don't see a reason to do more than one container or like as few containers as possible.
Right.
Because it's 1-to-1. So it's like, and and with the container you have to have an air gap between each container. So
yeah, and since you only have one person to load, like it's just I don't see how it would be faster to load more little containers.
Right, because I was thinking if we had like everyone on the team that could do it, we could just have like the same kind of like a similar idea, but just have multiple different containers that you could clip on.
Like a container per person.
Right, and create like kind of like a rib structure on that plane where we have like one container, then the next container, the next, and then continue up towards the.
Wait, isn't it one person that's loading the whole thing?
Yeah.
Okay. And for securing the container to the body of the plane, I feel like it's not hard at all. Like the Django blocks, I looked it up. They're like super light, each one, and then the container requirements that it has to be at least 2 ounces, and 2 ounces like not much.
Yeah.
So I can't like we could probably use like magnets or velcros or anything like a little bit of snap-on thing like you were talking about earlier. I think anything. I think the longest time that it would take for a ground mission is probably what Sam was focusing on, or Vlado was focusing on, with the putting the blocks into the container.
Right, I think that's the. Yeah. Also, I would say we have to make sure that it's on tight because when Laird was talking, Laird and Jake were talking about the turns. We're doing like a 180 turn, and if we're trying to do it as fast as possible, that's gonna have some force on that container.
Yeah.
Rip
I mean, honestly,
it's so funny.
Create like a bomb.
Or it just drops the whole.
I'd suggest, so one idea I just had was if we do something similar to the U-channel plane, but like inverted, such that like it's a low wing with a open top. So that way, as long as we're pulling positive G's, they stay in.
I can see that. That's a good idea.
Like
And that way we can be a little lazier with our attachment mechanisms.
Definitely.
Also, there's no unloading in ground mission, right?
No.
So, like, it has to be quick to get in, but it can be slow to get out.
Right.
So that, like, I don't have an idea for how to use that, but it just might free something up a little.
Wait,
Yeah.
Laird,
And
do
so
we
it's
modify the Jenga at all? Or does it have to be standard?
The Jenga blocks are standard.
Damn you.
So
It's
we
like an
can't put magnets in them so like
Yeah,
self
next to
stack.
Yeah, that no modification to the Jenga blocks. And then usually AIAA doesn't like magnets generally. So I'm probably gonna hold to that.
The motors are full of them.
Okay, touche.
Like,
They don't like them as restraint systems.
No, unfortunately not.
So I think
Also, you're not allowed
Okay.
to restrain the Jenga blocks
more
around the net.
idea.
Yeah, I was also gonna say you can't restrain them.
No
using a
noose.
Yeah.
Yeah, you can't use a noose.
Damn it! You preempted me.
God, a couple. It was our freshman year, right? Yeah.
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 The payload was like passengers with a cylinder.
Oh wait, no, that was sophomore year.
Was it last year?
Yeah.
Oh, it was sophomore
It was
year.
last
Yeah.
year.
Freshman year was footballs and
You're right.
random.
You're right. It was like a cylinder with like a ball at the top with like a little neck area to simulate like a little cylindrical
Literally
passenger.
looks like a wooden person doll thing.
Yeah.
Yeah.
With no face on it until you add one.
And someone asked in the Q&A, can we restrain the passengers around the neck? For example, a noose.
Wait, I
and-
think there was a picture, right?
There was no
They had-
picture. Was there?
I feel like there was a picture.
Pretty sure there was. And it wasn't like noose enough to like going up because they weren't like literally gonna hang them. It was just to go like back to like a seat structure basically. But
Yeah.
it was bad.
So AIAA was like, no, obviously not. That's ridiculous. Like, don't be a dumbass, basically. But the problem is that would like a latching mechanism would be the like most obvious way to restrain those passengers. And we were like, whoever phrased it as a noose
Is
is the worst.
But yeah, like
Wait.
humans have waists and they can bend there. So you can use a lap belt on a human. You cannot use a
Thing is,
lap belt on a cylinder.
Wouldn't that be the second most obvious? Like, it seems to me like the most obvious would be a lid, as in just like push down on the head such that it stays in place.
Yeah, that's what we did.
That's
Ultimately.
what we ended up
That's
with.
what everyone else went with.
Like, if they won't let you hold it by the bottom of the head, hold it by the top of the head.
Please attach your mandatory airline provided helmet.
I gotta head out because I have something else to go to. But thank you for the presentation, Laird.
Yeah,
and
for
I'll
sure.
see you guys Saturday.
Understandable.
Yeah, thanks for coming. See you
All right,
Saturday.
All right. Thanks, Preston. Have a good evening.
Yeah, see you guys.
See ya.
Yep.
I gotta go shortly, but I'm good for right now. But yeah, you guys have any other ideas for planes? I mean, we're kind of going off one design right now. So if that
And-
fails,
I mean, I'm pretty sure Laird didn't go into this very much, but you don't have that much more information in the direction that you're going in right now than you did after the last meeting, because you're mostly talking about like configuration and like that angle of design. But you could try potentially to start guessing basically at like performance design.
Yeah.
Right.
I mean, I honestly, it would not surprise me at all if the big plane turns out to be a good design point. Just because of the whole V cubed term.
Yeah. but you just gotta do math to find out. That's the
Yeah.
that's how
That's
it be.
worth Jake.
Yeah.
God damn. Just let us dream.
Yeah. So what I
You're
would
welcome
encourage,
to.
and I'll send a message about this in the Slack as well, along with some code resources tomorrow, is like taking a look, if you're interested, at the code that's already there. I am gonna, like, on Saturday, I'll kind of show you what code we have, and I'll send some code in the Slack soon, or tomorrow sometime, and just start playing around with it, like playing around with the numbers, see what happens if you plug in some ridiculous shit, and like that's a good place to start as well. So
Wait,
See you, Andrew.
Bye,
See you
Andrew.
Saturday.
Yep.
Thanks for coming.
Yep, thanks, Third.
yeah,
I forgot one thing, which is we should make it axisymmetric.
Of course, Vlado
Vlado-
says it has to be axis.
Vlado, you're gonna love this. You're gonna love what I did in spacecraft design today, or like spacecraft attitude, dynamics and control. Let me find my notes.
Vlado, if you can design you know what's even better than an axisymmetric plane? An isotropic plane. If you can design an isotropic plane, then I will fly it.
We were modeling axisymmetric spacecraft today, so
In the shape of a vase,
in the shape of an arbitrary axisymmetric shape, Jake.
aka
It's a vase.
If it's taller than it is wide, it's automatically a vase.
Indeed. Well, no, if
I
it's
mean,
taller than it is wide, it's oblate.
Thing is, though,
AKA a vase.
that's we all know that's a vase. Like,
It's true. It's true.
If it's wider than it is tall, it's a dish.
Indeed.
All right, Laird, good luck
Wait,
on
so
your
What
test.
a bowl.
So wait with that.
It's only a bowl if it has a rounded bottom.
Indeed.
and
it has
doesn't
to be
come in
hollow,
at all
right?
at the top,
'Cause-
right?
Well, all spacecraft are hollow, Johnny. Everyone knows that.
Well, no, I was saying
What's
like,
the definition
we're
of a
taller than
spacecraft?
we are wide. So are we?
Yeah.
We're just vases.
Well, but
Yes.
You're
yeah.
just a vase that's not being used yet.
But we're unfortunately, I mean, I guess you could assume
we're actually
axisymmetric,
donuts, though.
especially if you assume that we're a passenger.
I was assuming that because it's a vase, it's not a donut, so it doesn't have any through holes. But
Indeed.
I mean, in
Indeed.
space, your water automatically globs together and sticks to your flowers, so you don't necessarily need a bottom. It could be a donut.
That's true. That's true.
Not that the water would keep your flowers alive, but you could try.
Well, but then like it would also freeze dry them, so like they probably wouldn't.
They're both
really
alive
degrade.
and not alive.
Also,
Like,
I do
they'd
not
be
need to
dead,
be
but they
recording
wouldn't really
still.
degrade, right?